I'm David Newman from Wells Fargo, as you just said. I focus on the future of data at Wells Fargo. I lead an innovation R&D group. I also chair the Financial Industry Business Ontology initiative for the financial industry. So what I'm going to talk about is actually not specifically what we're doing at Wells Fargo. I can't disclose that, but I'll talk more generically about a variety of capabilities. So I'm going to cover a little bit about the challenge of data in our legacy environments. I'm going to cover what we believe is the future of data is based on ontology. I'm going to talk a bit about knowledge graph technology, which is a very simple formula. Ontology plus machine learning equals knowledge graph. And then I'm going to follow up on a bit of where we see the future of data further evolving, which is in an area called distributed semantic representations. But first, let's talk about the current state where we have tremendous challenges in our legacy data environment. So looking at this chart over here, you could see that we start with having many, many different parties participating in defining data in very siloed lines of business organizations where we see an explosion of very bespoke physical data types and columns, very difficult to herd the data cats. We have platforms where we define our logical and conceptual models, which are different than the actual physical schemas with databases that have to be built by DBAs. This ends up in a very difficult environment that's highly challenged, where we also have to take the knowledge from the business and encode it in many, many disparate, bespoke application programs that are all different, that all have to be tested differently, but quite often we see the common logic, the common specifications across these programs. That results in tremendous cost and expense and risk of error. Moving to where we believe the direction is with knowledge graph is a whole dramatically different environment where we create a layer of knowledge over all of these bespoke physical data sources so that we could let this layer of knowledge basically describe the concepts that align to the underlying physical data sources, so we don't have the challenges of identifying all the bespoke data for integration purposes. And also, this layer of knowledge will contain a lot of the requirements and specifications and concepts that would otherwise be coded in application programs. So we're moving much of this into this knowledge layer, which essentially results in improvements in standardization, improvements in precision, data quality, much more benefits in terms of ultimately faster time to knowledge, lower costs. So this is all where we see. So the starting point, as we heard in the prior presentation, is the ontology. And ontology is the specification of a conceptualization. In this example, we could look at a representation of an interest rate swap, which gives us the ability to define the specifics of the concept in a language that's reusable and standardizable, where we could look at the different parts of this interest rate swap, thinking of it as the equivalent of a molecular structure. It has a very unique signature that we could define in the ontology, and the ontology will then remember and understand what this particular signature is, and we'll be able to draw an inference on the kind of asset or the classification of this type of structure, which is a particular interest rate swap. So this formula, these molecular structures that we translate into a common standardizable language for finance, is something that we're developing under the auspices of the Enterprise Data Management Council. We're creating the standardizable, reusable, open source ontology for the financial system called FIBO, for the Financial Industry Business Ontology. So what FIBO is this ontology that is architected using this notion of the contract as the central element of the architecture, because we see that most financial instruments, if not all, are really represented using this conceptual scaffolding of a contract where there are provisions and terms of a contract that form the backbone of most assets and products and financial instruments, such that you could see the root concept at the very top is contract, and at the very bottom you could see in this example is an interest rate swap, and it rolls up conceptually up to the contract so that we can draw these inferences and leverage capabilities like inheritance, where the variety of representations and relationships at the contract level are inheritable all the way down to the very lowest level, which also allows us to ask certain questions because we can follow the standard formula based on the ontology, where we might ask an aggregation of what are all the positions across the derivatives instruments in the company. And it's an easy roll-up. It's very, very different than what we would have with a relational model, where we may have many, many, many types of bespoke tables that we would have to compose very complex SQL to join all of this information together to get an aggregation. You can do aggregations very easily with high precision using ontologies. You could roll all the way up to multiple levels. So the ontology also forms a basis for this knowledge layer, where in contrast to the conventional relational systems where we see an explosion of bespoke columns, very similar to what was mentioned in the earlier presentation, where we have different labels, let's say, for a credit card identifier through varieties of columns and tables, we're able to use the knowledge layer to use this hierarchy, in this example, an account identifier at a top level of abstraction. At the lowest level, we may have a credit card account identifier. These can be mapped to all of the different bespoke column names so that we could organize it better. And then we can also add certain relationships at the top level. So an account identifier, we can say has an information security classification of confidential. Therefore, the set of all things that are subclasses of an account identifier, like a credit card account identifier, is therefore also confidential. Therefore, all of the bespoke columns that we've mapped to will be inferred to be confidential. So this also is similar to the use case mentioned earlier. This is a way of how do we easily solve the data privacy challenges for GDPR, as well as the California Consumer Protection Act. So beyond having this layer of knowledge to represent various columns, this layer of knowledge can be further expanded, where we can define a variety of ontologies that can ultimately all link together. And this is really, we get the tremendous power of a knowledge graph, where we can basically infer certain links and relationships between many of the different siloed sets of data in the company, where we can begin to see certain relationships that we would not have seen otherwise without a lot of heavy computational effort. So the knowledge graph provides a basis for what we would call a semantic data lake, where the whole process is where we would have a set of columns where we've mapped to a common data catalog, so the knowledge layer representing all of the different bespoke columns. This provides a catalog of all the information in the varieties of data sources that we could then utilize various processes to ingest into a semantic graph database. So we can use an ETL process or an ELT process to load the semantic graph. We're not yet at the point where we're doing virtualized graphs. Now this semantic graph now becomes a common harmonized model by which we can link and integrate disparate data, harmonize it, and then be able to export it to varieties of target sources. So a knowledge graph now is also a key enabler for machine learning. So when we look at artificial intelligence, knowledge representation and reasoning is one of the legs of AI. So we have the ontology as an example of that. Some of the other legs of AI, machine learning, of course, deep learning, which is a kind of machine learning, natural language processing, and the goal is to leverage all of these together. So what the knowledge graph does is it provides a way to link and unify many of these other aspects of the AI space because it will allow for much greater underlying precision in many of these other forms. Let me explain. So knowledge graph is a way where we can ultimately have far better improvements in feature engineering for machine learning. Again, where we have many of these disparate data sources, one of the challenges of the data scientist is the wrangling of the data. Allegedly, around 80% of the data scientist's time is spent in collecting the data, making sense of it. The knowledge graph provides a way to fast forward out of that kind of quagmire and use the knowledge graph as a way for better data linkage and harmonization to create the feature sets based on the knowledge layer, based on the higher level concepts. We can ask the knowledge graph to pull the different data sources together that form the feature set for machine learning. Secondly, there are capabilities within the knowledge graph where we can define a reusable, standardizable data quality language to do data validation and constraint checking to make sure that the quality of the data from these disparate sources is golden and perfect. Otherwise, we use something called shackle, shapes constraint language. And then next is data classification and inference processing, where in a normal standardized feature set from relational sources, we again simply have a feature set of bespoke information that is not tied or linked together. Using a knowledge graph, we could draw inferences about certain relationships that exist in the data to get a much more robust output that is much more meaningful so that we can have improvements in machine learning. So moving forward, we can see that knowledge graphs can further ingest machine learning output. So we can see a basic standard semantic knowledge graph, an operational knowledge graph from the ontology that we could converge with certain outputs of machine learning that are basically different forms of probabilistic associations. The convergence of those two will represent what we could call a hybrid knowledge graph, where we take the inferences from machine learning and we tie that together and use the structure of the graph to show certain relationships. So let me explain. So here we'll have a small subgraph of a customer and customer A, person A, and variety of relationships associated with this customer. We then have customer B, person B, and a set of relationships associated with this person. We can apply various capabilities in the data mining and the machine learning space called entity classification and link prediction and entity resolution, where we can associate certain algorithms that can predict equivalence between the different nodes, where we can come up with a prediction of high levels of confidence that can only have occurred through looking and iterating through the nodes and doing a variety of processes like clustering and cosine similarities. But this also positions us to do other kinds of inference processing in a graph where we could trigger a whole new node, in this case, let's say a household, where these particular nodes do not represent equivalence, meaning the same person, but perhaps we can see that they're different people, but the address and other related information is the same. We may infer they reside in the same household. Or we may also draw inferences that they may know each other and create social relationships in this graph, as well as they may also be members of the same family. And we could represent that with a level of confidence where we can then do various types of sparkle queries against the graph, as in the prior example, where we could ask for different customers that, let's say, have a probability exceeding a certain threshold of 0.995 that may buy a move-up home in the Bay Area in the next year. So we combine the probabilistic associations with the relationships in the graph to get much greater precision. So one of the big challenges in machine learning is to be able to use numeric representation to identify semantic similarity. So the machine learning doesn't operate well with strings. It operates well with numbers or numeric representations. So the challenge is taking this stringified information and transforming it into some numeric representation or vectorization that a machine learning algorithm can really understand. So what one can do is use the ontology as a way to create a training set for machine learning by iterating through the ontology and basically transforming the concepts in the ontology to a set of text that we could then input in some of the conventional machine learning algorithms like word2vec, which basically takes a set of words and basically predicts their semantic relationships and generates what's called a word embedding, which is a vector of numbers that have semantic meaning that a machine can understand at this point. So we're transitioning now to a form where a machine can understand, and what we've generated is what's called a concept vector. So here's an example. It's not a Milky Way galaxy, but it's a representation of the FIBO ontology, where we're able then to look at different classes of financial instruments that have been translated into this multidimensional vector space that we've reduced down to 2 dimensions so that it's easy for people, humans, to look at. Machines get it right away. We can see bonds clustered together, interest rate swaps clustered together, corporations, partnerships, LLCs, different types of business entities clustered together, and so on and so forth. So this is an example of an empirical exercise where it demonstrates that one can actually take an ontology and translate it into vector space. Now, that's step one. Step two is now taking these concepts, which represent the vertices or the nodes in the graph, and now begin to predict the links or the relationships between these nodes to get greater specificity in relationships. So here is an example of one form of interest rate swap that we covered. And we can translate this into vector space. So a fixed float interest rate swap has a unique signature in vector space. A float-float interest rate swap has a different signature in vector space. So you could take these instruments and translate them in a form that machine learning algorithms can understand. So think of it also as a way of taking customer information and translating it into vector space. So here's an example where we can take a person who's stating something, an intent. We could translate it into vector representations, and then the machine learning algorithms then can understand the intent and then predict the best recommendation to resolve the customer's challenge. So in conclusion, what we're doing is we're starting off with a first-of-a-kind model. We're transitioning to a very novel infrastructure that leverages that model so that we could realize various insights. So that model, again, is the Financial Industry Business Ontology and other corporate enterprise ontologies. We can create a semantic data catalog, a semantic data lake, and then translating that ontology into vector representations. So some of the use cases that are solvable in this architecture: data privacy, improvements of customer knowledge, risk management, and many others. So in closing, ontology and knowledge graph capabilities are ready for prime time. They're ready to jump into the water. And it's a prerequisite really for transformation of the enterprise data fabric into the next generation. Knowledge graphs will not necessarily replace legacy relational technology, but it will supplement it. But it does require an in-depth amount of training to get there. So I would suggest that those of you that have not yet started on this journey start the journey, train people in-house as best you can, and start now. Thank you very much.